Hello and welcome to this lecture. We are going to see two proofs for why eigenvectors, eigenvalues exist. The first one starts with a point of view of matrix powers acting on a vector. Even in the R2 to R2 case we had this proof. So I am going to sort of repeat it in the more general case. So once again my operator T is from Cn to Cn and I pick some non-zero V. Okay, you can pick any V you like. Okay, whatever vector you want you pick, but it has to be non-zero. And then you consider these n plus 1 vectors. What are the n plus 1 vectors I consider? V, T of V, T square V, so on till T power n V. Okay, there are n plus 1 vectors here, right? Now here comes the interesting observation. These are n plus 1 vectors in an n dimensional space, and of course maybe Cn. Okay, I put Fn here, Cn. So they are linearly dependent, right? These n plus 1 vectors end up being linearly dependent. Right, n dimensional space, n plus 1 vectors, they have to be linearly dependent, right, cannot be any other way. Okay, so what does that mean? Means there are scalars a0 to an, not all 0, such that an tn t power n v plus so on till a1 t of v plus a0 I v, I am just emphasizing the I here for completion, equals 0. I is the identity operator. Okay, so this equation is true. This almost looks like a polynomial, right? It looks like a polynomial, but except you have this t power n's, t and all these operators floating around. These are not just variables. Okay, so the trick is to convert this into some sort of a polynomial equation. Okay, so first is one of these a1 to an is non-zero. Okay, why is that? Why should I mean, is it not enough if a0 is non-zero? Because if all of this a1 to an is 0, you get a0 times v is 0, which makes a0 also 0, right? Because v is non-zero. Okay, so if a0 v is 0, then a0 is 0. So all of these cannot be 0, one of them has to be non-zero. Okay, so keep that in mind, one of this a1 to an has to be non-zero. Okay, that's okay. So we will rewrite this equation by taking v outside, right? an t power n plus so on till a1 t plus a0 I times v equals 0. So v is like sort of going to distribute over this in an easy way. So we write it like this. Okay, so notice this whole thing is one operator, right? There is a non-zero v such that this operator, this big polynomial operator in T, when it operates on v, I get 0. So what does that mean? When you have an operator and a non-zero vector v such that the operator acting on v is 0, then this v should be in the null space of this guy, right? That seems to be powerful, but how do we simplify this further? Okay, so v is in the null space of this guy, but how do I simplify this further to try and understand it better? Okay, so here we are going to connect with polynomials. Okay, so how do we connect with polynomials? Ignore for now that this t is some dangerous looking operator, simply replace it with x, some variable that we know. Okay, an x bar n plus so on till a1 x plus a0. There is a theorem called Fundamental Theorem of Algebra, which guarantees that a polynomial of degree n with n complex coefficients, the coefficients complex, it has in this case m complex roots. So this m is the degree of the polynomial. Okay, so this an could be 0. So I don't know, this polynomial may have degree m, and this m is greater than or equal to 1, right? It's between 1 and n, because one of these guys is non-zero, I know for sure. So the degree has to be at least 1. Okay, 1 to m. So some m is the degree of this polynomial. If you have a polynomial of degree m, there are m complex roots. So here is where the complex numbers comes in. I said you have to use complex numbers, no, because the Fundamental Theorem of Algebra guarantees roots only in the complex numbers. It's not real anymore. Okay, so you have lambda n, lambda 1 to lambda m. So this is the degree m polynomial, and it has roots lambda 1 to lambda m. What does that mean? This polynomial factors into some constant c multiplied by x minus lambda 1 so on till x minus lambda m, and the c is non-zero. Okay, so this is polynomials, all of you may be comfortable with this. So what does this equation mean? When I multiply these products out, multiply x into this is x squared minus lambda m x minus lambda 1 x plus lambda 1 lambda m. I do all those products and multiply them out, coefficient to coefficient these two will agree. Okay, all those functions of lambda that you will get in the coefficients will become equal to ai's here. Okay, so that's what this means. When you multiply and simplify the right hand side, you will get exactly the left hand side. Now, you're noticing this x here as a variable. It turns out instead of x, I can use t in this expression and then use my knowledge of matrix algebra to try and simplify. Okay, so notice what happens here. Let me just quickly show you a couple of examples. Okay, so you have, so let's say x minus, we go to the black one. You have x minus 1 times x minus 2, let's say. If you do t minus 1 times t minus 2, you get the same answer, right? So you get x squared minus 2x minus x plus 2, which becomes x squared minus 3x plus 2. If you do t minus 2 into t minus 2, the operator, you can just multiply the same way, right? So t into t is t squared minus 2t minus t plus 2. Okay, well, this is I, 1i, 2i. So I guess you get I here. So this just becomes t squared minus 3t plus 2i. So these two things sort of exactly match, except x gets replaced by t. So now we can imagine any number of multiplications will respect the same thing. So it doesn't matter whether you use x here or t here, c times t minus lambda 1 to t minus lambda I, right? Instead of this lambda 1s, I should put I here. This will become the same form as here with x replaced with t. Okay, so you can see how this happens very easily, right? So how do I simplify this guy? This equal to 0 is the same as t minus lambda 1i dot 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 t minus lambda mi v equals 0. A bunch of products of matrices became equal to 0 instead of one big ugly polynomial. Looking at that. Okay, and in this form we can now use the null space property and come up with a very interesting result. Okay, so for a non-zero v, when you put all together, you are getting t minus lambda 1i dot 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 t minus lambda mi v equals 0, which means this v belongs to the null space of this product, which means for at least one j, t minus lambda ji has to be singular. One of these lambda i's has to give me a singular operator when I do t minus lambda ji, right? Null space has a non-zero vector. Okay, why? Because if all of them are invertible, then null of t minus lambda 1i product will be 0. It will not have a non-zero value. This contradicts the v, so at least one of them has to be invertible. Okay, that's the idea. So there exists a complex number lambda such that null of t minus lambda I is not equal to 0 or t minus lambda I is singular. Okay, so this is one proof to show that for any operator t, there is at least one eigenvector and one complex eigenvalue, one complex eigenvector and one complex eigenvalue. So that is guaranteed. So this proof is a elegant and simple proof in some sense. It doesn't use any other complicated notions. The next proof we will see uses the idea of determinants, and that we'll see in the next lecture. Thank you very much.